All right, we have two more examples to do. Both of these are indeterminate forms that have this sort of exponential type of form to them. So there's three indeterminate forms that kind of fit this mold. There's 0 to the power of 0, infinity to the power of 0, and 1 to the power of infinity, which we discussed in the previous video. You know you're looking at one of these when you have a limit where you have one function to the power of another function, and the limit as x approaches a, whatever a happens to be, causes one of these three cases to happen. So we're looking at that here. If you notice, I have the limit as x approaches 0 from the right of tangent of 2x to the power of x. Now, if I were to plug 0 in directly, tangent of 0 is what I would have in the parentheses. That's equal to 0. And then I'd have that to the power of 0. So this is a 0 to the 0 indeterminate form. That's undefined. Direct substitution is not actually giving me a legitimate limit. So there's a specific way of handling these, and we're going to be using logarithms to our advantage here. What I'm going to do is take this expression and define y to be equal to the thing I'm taking the limit of. Y equals tangent of 2x to the power of x. And then if I were to take a natural log of both sides, I'd get the natural log of y equals the natural log of the tangent of 2x to the power of x. And the purpose of taking that natural log is to handle this exponent, because I have a logarithm property that allows me to move that exponent out to the front, so that this becomes it becomes this, x times a natural log of tangent of 2x. Okay, so what I'm going to be doing is taking the limit as x approaches infinity of this. Okay, the limit as x approaches, or not infinity, I'm sorry, 0 from the right, okay, of this expression, x natural log of tangent of 2x, okay? Now, again, direct substitution still doesn't work here because I end up with an indeterminate form, but I'm going to rewrite this so I can put it in the form of an indeterminate form that's more useful. If I were to do this, the limit as x approaches 0 from the right of the natural log of tangent of 2x over 1 over x. This is equal to this. Okay, I'm just dividing by the reciprocal of x, which is the same thing as multiplying by x. Look at what happens if I try direct substitution now, or if I try taking the limit as x approaches 0 from the positive side. As x approaches 0 from the positive side for tangent of 2x, this thing in the parentheses is going to 0, but from the right, from the positive side. I know that the natural logarithm as x approaches 0 from the positive side goes to negative infinity. Similarly here, 1 over x, if I take the limit as x approaches 0 from the right, this goes towards positive infinity. So I have like a negative infinity over a positive infinity, which we simply refer to as the infinity over infinity indeterminate form. Remember, this, even though there's no negatives anywhere, this indeterminate form can have negative infinities here, or in both places. So this is now in a form that L'Hopital's rule would apply to. So I'm gonna do that. I'm gonna apply L'Hopital's rule. Limit as x approaches 0 from the right. Now the numerator, remember if you have a composite function, but it's a natural log of tangent of 2x. And we've done a lot of these before, to where you don't even need to think of it in terms of the chain rule. It's just the derivative of tangent of 2x, which is 2 secant squared of 2x over tangent of 2x. The derivative of 1 over x is equal to negative 1 over x squared. Okay? Now, I'm going to do a little bit of rearranging here. So this is the limit as x approaches 0 from the positive side. Since this is, I'm dividing by a reciprocal, I can multiply my numerator and denominator by negative x squared to move the negative x squared up here. Okay? Now I can also multiply my numerator and denominator by tangent of 2x to get that tangent of 2x out of the denominator there, and in this denominator down here, it becomes tangent of 2x. That would leave me with a 2 up here, so I'm going to squeeze the 2 in right there. Secant squared of 2x. But secant squared of 2x is the same thing as 1 over cosine squared of 2x. And then I can, once again, multiply numerator and denominator by cosine squared of 2x to move that down here, cosine squared of 2x. So I did a lot of simplifying all in one step here. And I have a little bit more simplification that I can do. This is equal to the limit as x approaches 0 from the positive side of still negative 2x squared here. But think about this for a moment. Tangent of 2x is equal to sine of 2x over cosine of 2x. That's how we define the tangent function. And the cosine of 2x in the denominator, if I were to convert that tangent of 2x into that quotient, would cancel with one of the cosines showing up here, cosine squared of 2x. I'm going to lose one of those. So I'm left with sine of 2x from my tangent and one of these cosines of 2x right here. Okay? Now I'm going to take it one step further. This, my denominator, very closely resembles the double angle formula for sine. I'm going to say, if you don't remember the double angle formula for sine, it's incredibly useful in calculus. We use it a lot in Calculus 1 and even more in Calculus 2. But if you need to review it, this is the same thing as 1/2 sine of 4x. Okay? I'm going to go even one step further, multiply my numerator and denominator by 2 just to eliminate that 1/2. I actually don't really need to do that, but I like the way that that looks more. So I'm going to write that as negative 4x squared over sine of 4x. Now notice I've only used L'Hopital's rule one time, and that was getting from here to here. Everything else has been a bunch of simplifying. And I don't see any more simplification that I could do. So now let's take a look at the limit. If I try direct substitution again, plugging a 0 into my numerator and denominator, you're going to see that you have yet another indeterminate form. It's a 0 over 0 type this time. So that would imply that I need to use L'Hopital's rule. Again, this becomes the limit as x approaches 0 from the positive side of, this would become negative 8x, and down here I'm going to get 4 cosine of 4x. Now this I can evaluate using direct substitution, because if I were to plug a 0 in, I get a 0 in my numerator, but a 4 in my denominator. Cosine of 0 is 1 times 4 is 4. That's equal to 0 over 4, or simply 0. Now, you're not done here, because you have not found the limit of the original function. You've not found this limit yet. What you've found is the limit as x approaches 0 from the right of the natural logarithm of that. So I need to somehow use what I have to get back to the original limit. And what I'm going to do is come back up here. If I have the natural log of y equals this expression right here, then I can bring this back a step by taking e to the power of both sides. So for example, if I wrote e to the natural log of y, that would equal e to the natural log of tangent of 2x to the power of x, which of course would then cancel those out. Okay, what is that? Tangent of 2x to the x. So this is equivalent to this, okay? And notice I could have written this at the very beginning. The limit as x approaches 0 from the positive side of the natural log of y equals that, okay? So how am I going to use that now? Well, if I want to find this, the limit of this guy as x approaches 0 from the positive side of tangent of 2x to the power of x, that's equal to the limit as x approaches 0 from the right of this equivalent expression, e to the natural log of y. However, we know from the fact that e is a e to the x is a continuous function that I can bring the limit up here. Limit as x approaches 0 from the right of the natural log of y, and I have found that here, okay? We know that limit. It comes out to 0. So this becomes e to the power of 0, which is equal to 1. That's how these sorts of limit problems work. I think these exponential types are generally the most complicated ones because of all the manipulation you have to do, all the algebraic manipulation, the use of that logarithm to make the limit work. Okay, I want to do one more example like that, and it's going to follow essentially the same logic, the same approach. It's just going to be one more example that we can get under our belts here. So once again, I'm going to define y to equal the expression I'm taking the limit of e to the x plus 10x to the 1 over x power. Then I'm going to take the natural log of both sides. The natural log of y is equal to, I already know what's going to happen with that exponent property, so let's jump ahead to that. 1 over x times the natural log of e to the x plus 10x. Notice I could also write that this way. Natural log of e to the x plus 10x over x, which is convenient because, again, we need this to be a 0 over 0 or an infinity over infinity indeterminate form in order to use L'Hopital's rule. So getting this in the form of a quotient is ultimately where we would end up anyways. So now what I'm going to do is take the limit, just like the previous example, as x approaches infinity, that's where we're going this time, of the natural log of y, which would equal the limit as x approaches infinity of this natural log of e to the x plus 10x over x. Now in this case, we're looking at an infinity over infinity indeterminate form, which is easy to verify. The function in here, e to the x plus 10x, as x goes to infinity, everything in the parentheses will go to infinity, and the natural log of x as x goes to infinity also goes to infinity. So my numerator is going to infinity, my denominator is very clearly going to infinity. So this means I can apply L'Hopital's rule now that I've identified that it's one of those two types of indeterminate forms. So this is equal to the limit as x approaches infinity of, now the derivative of my numerator is going to be the derivative of the stuff in parentheses, e to the x plus 10x over, plus 10, not 10x, that's the denominator, plus 10x down here, over 1, because that's the derivative of x. Or, with some simplification, I don't need the 1 there, I can just write that this way, e to the x plus 10x, okay? And then we look at what we have. Can we evaluate this, or do we need L'Hopital's rule again? Well, if I take the limit as my numerator and denominator both go to infinity, I end up with yet another infinity over infinity indeterminate form. So that's okay, I just need to use L'Hopital's rule again, which I'm allowed to do because it's the correct form for that. So, applying L'Hopital's rule, my numerator has a derivative of e to the x, my denominator is going to look like e to the x plus 10, okay? But yet again, we have an infinity over infinity indeterminate form. So I need to use L'Hopital's rule yet again, a third time. This becomes the limit as x approaches infinity. E to the x is its own derivative. E to the x plus 10 will become e to the x after taking a derivative. And then here, I can just divide those and simplify. This becomes the limit as x approaches infinity of 1, which is equal to 1. It's a constant function, right? So now that we've established that, remember we're not done yet. Because what I've done up here, since natural log of y is equal to this, that's going to imply that y, if I take e to the power of both sides, so let me do that this way, e to the power of the natural log of y is equal to e to the x plus 10x to the power of 1 over x. So if I want the limit of this, the limit as x approaches infinity of e to the x plus 10x to the power of 1 over x, that's the same thing as the limit as x approaches infinity of e to the natural log of y. I can bring the limit up into the exponent now, because this thing I've evaluated already and found that it was equal to 1. So this becomes e to the power of 1, or simply e. Okay? So these, like I said, these tend to be the most complicated examples from this section, but this is the general approach that you want to take when you're doing those. So this is going to wrap up section 4.4.